we're going to look at, so this is the beginning of chapter 8. We're going to start looking at a new type of function now. We're going to start looking at rational functions. So what is a rational function? Well, a rational function basically is just referring to a ratio. Alright, so rational means ratio. And we kind of did this a little bit earlier in the course, but a ratio is just the comparison of two quantities, A over B. But the difference here is that A and B are going to be replaced with polynomials. So basically all a rational function is a function that could be written like this. And P and Q are just polynomials. So yeah, that's all a rational function is. It's just a function of a fraction, where the top and bottom of that fraction are random polynomials. And here's 3 examples of a rational function. As you can see here, this is a trinomial. This is not a quadratic, because this is to the third power, but this is a polynomial divided by another polynomial. This is a binomial divided by another binomial. This is a constant divided by a monomial. These are all examples of rational functions, and you could literally think of infinite types of rational expressions. Now, technically, these are rational expressions because they're not equal to anything. That's what I say in this note right here. These are rational expressions, not functions. It's only a function when f of x is equal to something. So, for example, these are expressions, like I just mentioned. A function a rational function is if I let f of x equal to one of these. So for example, I'll just use the smaller one. Now it's a rational function because it's equal to f of x. This is a rational expression. This is a rational function. That's the only difference between the two. So, that's what the definition of a rational function is. We're also going to look at other things. We're going to look at how to simplify rational expressions and finding the domain of a rational function. Okay, so just as like a warm-up, how do you evaluate rational functions? Well, it's very easy. How do you evaluate any function? You just take the input and plug it in and find the output. So I want to evaluate this rational function at 6. So all you do is plug in 6 for x. So you get 6 minus 5 over 6 squared minus 4, which is 1 over, squared is 36, minus 4, so that's 1 over 36 minus 4, which is 32. So that is the function. Evaluated at 6 gives me 1/30, or 1/32, or 1 over 32 as its output. You evaluate any kind of function the same way. Take the input, plug it in to find the output. So, yeah, so that's what rational functions are. They're just, rational means ratio, which means fraction. That's what it is. And a rational function, takes this form. So, to go on to the next page, what we're going to do is we're going to look at the domain of a rational function. Now, if you remember, what is the domain? So, when we first talked about domain and range in the beginning of the course, the domain is the set of all possible, and I emphasize the word possible, values of x. So, having said that, we want to look at, when we're looking at the domain of a rational function, we're trying to find the set of all possible values for x, and we want to see if there's any inconsistencies that may arise. Now, when we're dealing with a rational function, there are some values of x that could be undefined. Why is that? Well, you know from basic mathematics you cannot divide by 0, right? I say it down here. We cannot divide by 0, so what does that mean? Well, that means that if I have a rational function, which is this form right here, it means the polynomial that's in the denominator, right? Since a rational function has a denominator, duh, because it's a ratio, the polynomial in the denominator cannot equal 0. So that means q of x cannot be 0. So that leads us to the following note or definition. The domain of a rational function, which is this, is the set of real numbers of x. And here's the thing to remember, right here. Except the values of x that make q of x equal to 0. So whatever this little guy down here is equal to 0, for whatever values of x that q of x is equal to 0, those points of x are not included in the domain. So what we do is we assume the domain is all real numbers. We assume that the domain is all real numbers, and then what we do is we look for the values of x which make the denominator 0, and we take those away from all real numbers. What's left over is the domain. These values that make x, or these values of x that make this 0, are bad points. So find the bad points which make q of x equal to 0. And then we remove from all real numbers to get the actual domain of the function f of x. So assume the domain is all real numbers. We find the bad points, which is the equation q of x equals 0. Take them away from the all real numbers, and whatever's left over is the domain. So let's look at a few examples here. So I want to find the domain of the rational functions below. Okay. Well, if I look at this function, so I have x minus 4 over the quadratic x squared plus 5x plus 4. So if I assume the domain is all real numbers, all right, I want to find the values of x that make the denominator 0. I don't care about the numerator. You know, the numerator could be 0. That's fine, because if you have 0 in the numerator, then it's just going to be 0. That's fine. 0 in the numerator is perfectly okay. But we cannot have 0 in the denominator. Like if I took a number 4 and divided it by 0, you get an error message. You can't divide by 0. So you can't do it. Any number divided by 0 is no good. So what I want to do is I want to look at this equation. So the denominator cannot equal 0. So I want to find when the denominator is equal to 0. So I want to look at when x squared plus 5x plus 4 equals 0. I want to look at the solutions to that equation. That is what q of x equals 0 is here in the basic sense. So I just got to solve this equation. Well, how do you solve this equation? This is a quadratic equation. That was the topic of discussion in Chapter 7. So we could solve a quadratic equation one of three ways. Factor it, complete the square, or the quadratic formula. If you could factor it, definitely factor it. And as it turns out, we can factor this one. Which factors of 4 give me 5? We're using the AC method. Well, that's easy. So I have x and x because the leading coefficient is 1. And the factors of 4 which give me 5 are 1 and 4. And since they're both positive, both factors are positive. And that's it. And if you do the FOIL method here, you'll get back at this. So now I could just apply the zero product property and state x plus 1 equals 0 or x plus 4 equals 0, and then solve for x in each factor, which subtract 1 to get x equals negative 1 or x equals negative 4. Okay, so the domain if I want to describe this in words, the domain is going to be all real numbers, because remember, we assume it is all real numbers at the beginning. All real numbers except the values of x that make q of x equal to 0. Well, which values of x make this equal to 0? We just solved it. Negative 1 and negative 4. So all real numbers except x equals negative 1 or x equals negative 4. That right there is the domain of this function in words. There is actually a set notation you could use. Curly bracket. And you could say that x is in the real number system such that x is not equal to negative 1 or negative 4. So that's another way we could do it, illustrating the domain of a rational function. Let me extend this a little bit. It looks a little sloppy there. So yeah, but you know, words is fine. That's perfectly okay. If you want to do this with interval notation, so if I want to illustrate that on the number line, if all real numbers, you know, I'll put these bad points, I'll put them on here. So there's 0, negative 1, negative 4. Now 0 is not a bad point. 0 is perfectly fine. I just put 0 on here to distinguish negative and positive numbers. If I want to do this with interval notation, so the domain is all real numbers, which is the whole number line. We assume that, and then we remove these points from it. So that's part of the domain, but that's not, because it's a bad point. This is part of the domain, but negative 1 isn't, because it's a bad point. And then everything else, including 0, is part of the domain. So in interval notation, how do we describe this shaded line? Now, there are open dots there. They're not included in it. So in interval notation, we could do this as the following. So we have to describe three intervals here. This set, and this set. So what's the smallest value on this interval? Well, it's going to be negative infinity, right? Because this keeps going off forever and ever, all the way up to negative 4. But negative 4 is not part of it, so it's open. All right. This interval is from negative 4, which is open because it's not part of the domain, all the way out to negative 1, which is also open, and then from negative 1, which is open, all the way out to positive infinity. Those are the intervals that represent each one of these shaded regions on the number line, and that is a domain in interval notation. So yeah, these are just various ways you could describe the domain of this function, in words and in symbols, in interval notation. Let's look at the next one. So, again, same idea. I want to find when x squared plus 10 equals 0. I want to solve that equation. How do you solve this equation? Well, you can't factor it. You can't factor it because this is a sum, and a binomial sum doesn't factor. So what I could do is I could subtract 10 from both sides because there's no x term in here. So what I'll have is x squared equals negative 10. Now what do I do? Take the square root of both sides. So the square root of x squared is going to cancel, and then since I took the square root, I got to put a plus or minus out front. Negative square root of 10. Uh-oh. I want to simplify this. Let's do that. So since that's negative, I can factor out what? I could factor an I out, and I have I square roots of 10. Now could this reduce? Can I reduce the square root of 10? Can I factor a perfect square out of that? So the first perfect square is 4, that doesn't go into it, and then the next perfect square is 9. That doesn't go to it either. So no, I can't. So that's as far as that goes. So x equals plus or minus I times root, or square root of 10. Well, okay, so what we're saying here is that the values, these values right here, make the denominator 0. But what kind of values are these? They're imaginary. So let me say this. If we start from the beginning and we assume the domain is all real numbers, but we get imaginary numbers when we make the denominator 0, then what is our domain? Our domain is what? It's all real numbers. Remember, we assume that the domain is all real numbers, then we take away the bad points. But let's think about this. If I start with all real numbers, and I remove the bad points, which are imaginary numbers, what do you get when you remove imaginary numbers from real numbers? There's nothing that changes. You still have all real numbers, because these are two different sets of numbers. That's why the domain is all real numbers. So just because you have something down here doesn't mean you're always going to have bad points. Just keep that in mind. You have to check it though, because you know, when you're looking at a domain, you still have to see what is in the denominator. But in this case, the denominator leads to imaginary values for 0. So the domain is all real numbers. I can put any number I want in here for x, and you're going to get a result. You're going to get a result. Okay. So let's look at simplifying these suckers now. And basically, when you're simplifying a fraction, that's just saying you're doing what? You're writing a fraction in lowest terms, right? For example, if I have the fraction, I don't know, 21 over 28. How do you write that in lowest terms? Well, you factor the top and bottom. What are the factors of 21? 7 and 3. What are the factors of 28? 7 and 4. Right? So, since I factor the top and bottom, now I could factor 4 into 2 times 2, right? But that's not going to cancel out. But what is going to cancel out? The 7s are going to cancel out. And you're going to be left with 3/4. So we always write a fraction in lowest terms. You know that from basic math. The same thing applies to polynomial expressions or rational expressions. Same thing. You want to factor the top and bottom, which we know how to do, and then cancel out like factors. Just like these. They cancel out. So, all right, let's factor these. So, how do you factor the top? Well, the top is a quadratic. So we're going to factor it with the AC method. However, what should you always check this factor out first if you can? The GCF. Is there a GCF between 2, 6, and 20? There is. 2 goes into 6, 3 times 2 goes into 20, 10 times. So I could factor a 2 out of the top. Alright. What do I have left over? So I have x squared minus 3x minus 10. Can I factor a 2 out of 50? Yes, I can. 25 times, and 2 goes into 2 once. So if I factor 2 out of that, I get x squared minus 25. What happens to these 2's right here? They cancel out. So now I'm left with x squared minus 3x minus 10 in the numerator, all over x squared minus 25 in the denominator. Well, I got to keep going. This is a quadratic. This is a binomial. Actually, yeah, this is a quadratic. What is this down here? This is a difference of 2 cubes. I'm sorry, not cubes, squares. I'm an idiot. This is a difference of 2 squares. That's what I meant to say. So I want to see if I could factor the top. Well, I could factor a quadratic with the AC method. So let's see if that factors. So this is x squared. So I have x and x here. Which factors of 10 give me negative 3? Well, 5 and 2. Right? Now I just got to figure out the outside inside that gives me the right signs here. So I need negative 3. So if I have 5x and 2x, to get negative 3, the bigger one should be negative, right? And then this one should be positive. And negative 5 times positive 2 is negative 10, so these are the factors. Now how do you factor this? This is a difference of 2 squares. So you remember, that's a difference of 2 squares. What does that factor to be? A minus b times a plus b. So this factors to be x minus 5 times x plus 5. Right? This was the formula for the difference of two squares. So what happens now is, do I have any common factors that cancel out? I do. Everything inside the parentheses must cancel out. So everything inside the parenthesis is a factor. Okay? So the x minus 5, that whole factor cancels out with this x minus 5. So I'm left with x plus 2 in the numerator and x plus 5 in the denominator. Now, you cannot cancel out these x's. You can't do that, because this is addition in both cases. You're adding 2, you're adding 5. You cannot cancel out sums. You can only cancel out factors. This is multiplication. This is being multiplied by this. This is being multiplied by this. This is being added to 2. This is being added to 5. You can't cancel that out. You cancel out products of factors. You don't cancel out sums of terms. So since I can't cancel anything out from the top and bottom in this fraction anymore, that's it. This rational function simplifies to that. I don't know about you, but I'd rather work with this, or I'm sorry, I'd rather work with this than this. Now there are some, exceptions to like what the graph, like the graph of this function looks a little different than the graph of this function. If you were to graph them, there's not much difference, except there's there's a discontinuity. You would see something like, you look at the comparisons of these graphs in like MAT105 if you take that course, but in this course you just need to know how to simplify them. Alright, let's look at the next example. So, well, I don't have a GCF in the numerator, and that's a quadratic, so I know it's going to factor with the AC method. At least I hope it will, and it does. But what's wrong with the bottom? This is not written, first of all, there's no GCF, but this is not written the correct way. You have to write it in descending power. So let me do that. I'm going to write this as negative x plus 4. That's the right way to do it. Now, let's factor the top. So, x and x. Which factors of 12 give me negative 1? Well, 4 and 3. Since this is negative, the greater of the two should be negatives. Right? And this one should be positive, because this is negative. Negative 4 times positive 3 is negative 12. Now, if I look at the denominator, the leading coefficient should never be what? It should never be negative. So technically there is a GCF here. It's negative 1. Pull this negative 1 out of here. Remember, we talked about that when we did factoring. It's a very simple thing to forget about. When you factor a negative 1 out of here, what do you have left over? Well, if you factor a negative 1 out of negative x, you get positive x. When you factor a negative 1 out of positive 4, you get negative 4. Now, does anything cancel? You bet. X minus 4, that whole factor cancels out with that whole factor. So you're left with, now because this is a negative 1, I could really bring that up top, it makes no difference. So this is going to be x plus 3 over negative 1, which I could just write as, I could just bring the negative 1 up top and write it as negative quantity x plus 3. That's it. So, simplifying rational expressions is just a fancy way of saying factor the top and bottom, cancel out like factors if you can. If you can't, then it can't be simplified. All right. Let's keep going. So, the last thing I want to talk about is a new notation called the quotient function. So if you remember, we studied function notation. We looked at sum. Right, we looked at the sum notation for a function, right, which looked like this. We looked at difference notation for a function. That was sum. This is difference. Well, now we also have the product. Right. If you recall in your notes, these were the notations. Well, now we have a quotient function. We could just write it as f of x over g of x. So, there's actually two ways you could do this problem. If I want to evaluate the quotient function at 3, so by this definition, it's equal to f at 3 over g at 3. Alright, so I'm just going to plug 3 into both f of x and g of x. So when I plug 3 in here, 8 times 3 cubed minus 125 all over 4 times 3 squared minus 25. And now from there you could just do the direct computation. You're going to get some big numbers, but you will get the right answer. So 3 cubed is 27 multiplied by 8 is 216 minus 125 all over 2, so 3 squared is 9 times 4 is 36, so 36 minus 25. So the the numerator becomes 216 minus 125, which is 91 all over 11. Now, they're prime numbers, so 91 over 11 doesn't reduce. It's 91 over 11. Weird number, but that's what it is. So, that's one way you could do it. Another way you could do it is by writing this out using this notation. Replace f of x and g of x with the functions that are given. And you could realize that you could factor the top and bottom here, because the top here is actually a difference of what? Well, this is to the third power, so it's a difference of cubes. And the bottom is, well, it's a difference of, it's the second power, so this is a difference of squares. Because 25 is a perfect square, and 125 is a perfect cube. Now, we already know what a difference of squares factors to. We just did something like that. This is going to factor to two binomials, a minus b, a plus b, because this is a squared minus b squared. So this is right, and if I factor this, right, a squared minus b squared equals a minus b times a plus b. So what number squared is going to give me 4? Well, that's 2. And x squared is x. So I know both a's are going to be 2x. What number squared gives me 25? 5. Minus plus. Minus plus. So this factors to be 2x minus 5, 2x plus 5. Okay. Now what about the numerator? Now this is a difference of cubes. You might forget what this factors to, but it factors to a binomial and a quadratic. Remember the difference of cubes formula for factoring? So if you look in your notes, it's there. I think when we in chapter 6 when we did factoring, if you look at that, it's a minus b times a squared plus ab plus b squared. So, and again, just look in your notes. It's there. It's there. You just got to find it. Okay. So what are my factors going to look like? Well, sorry, just give me 1 minute. Sorry about that. So, my factors, right? So, what number cubed gives me 8? Well, you can use your a perfect cube. So, 2 cubed gives me 8, right? So, we know that 2 is the number. So, we know that A is going to be, right, 2. And then x cubed, well, that's x. So, I know that A is 2x minus quantity cubed. So what number cubed gives me 125? Well, that's going to be 5. Because 5 cubed is 125. 5 is a perfect cube. 2 is a perfect cube. I'm sorry, 125 is a perfect cube. 8 is a perfect cube. The numbers that give us those perfect cubes are 2 and 5. So that's going to be 5 cubed. Alright, so I know that this is A and this is B. So I just replace them in here and I get my factors for this. So A minus B is 2x minus 5. A squared is going to be 2x squared, which is 4x squared, plus A times B. So 2x times 5 is 10x, plus B squared, which is B squared. So 5 squared is 25. All right. So what we have here is this difference of cubes factors to be these two factors. Now this one is 2x minus 5. And this is a quadratic, 4x squared plus 10x plus 25. Now, I'll just say this to save time, but you would check to see if you could factor this with the AC method, right? So look at all the possibilities. So the factors of 4 are 1 and 4, 2 and 2, 25 is going to be, what, 1 and 25, 5 and 5. So you want to see which ones are going to give you 10. Well, as it turns out, this quadratic doesn't factor. It doesn't factor. So this is a prime quadratic. Doesn't factor. So in that sense, we're lucky. We don't have to factor again. So the whole factors of this difference of cubes is this 2x minus 5 times this quadratic. Now, under normal circumstances, you would go through without the AC method to do it, but I'm, if I wanted to factor this, right? You would go through, all right, the factors of 4 are 1 and 4, 2 and 2, 25, 1 and 25, 5 and 5. Here's a pair, here's a pair, here's a pair, and there's a pair. All right. Go through all those pairs and see which ones give you 10. As it turns out, none of them do. None work. Alright, so let's come back up here. So after all that's said and done, this factors to this, the denominator factors to this. Can anything cancel out? Yes, it can. 2x minus 5 cancels with this 2x minus 5. So I'm left with 4x squared plus 10x plus 25 in the numerator all over 2x plus 5. So since this factored, right, I could evaluate 3 in this function now. So basically I could plug 3 in and get this, or I could write it this way and then factor it and then plug 3 in later. So now I could plug in 3 into here. So when you do that, right, when you plug 3 into here and then 3 into here, so what I'm going to do is I'm going to store 3 into x, store x, going to type it in this one, 4x squared plus 10x plus 25, and I get 91. Hey, that sounds familiar all over. And then you store it in, 3 is already in for x, type in 2x plus 5. 11. So again, just to show you that a common factor is going to cancel out, you'll still get the same result. A lot of students do it this way because they don't like to do the factoring, but factoring is important. Do not ignore the factoring. And we're going to do a lot of factoring, don't worry. In the next few sections in this chapter, factoring will be done a lot, I can promise you that. So yeah, this first section is just a way to introduce you to some of the things that we'll look at when we deal with rational fractions. So the next few sections, like 8.2, 8.3, and I think 8.4 is going to look at doing operations with rational expressions, like adding them, subtracting them, multiplying them, dividing them, stuff like that. And yeah, so I think 8.2 is multiplying and dividing rational expressions. And then 8.3 is adding and subtracting, and then simplifying complex ones in 8.4, and then so on. So yeah, the rest of this chapter is just basic arithmetic with rational expressions and how to do them. Alright, so that's the first section of chapter 8, and that's the end of this video.